Good afternoon, everyone. I'm Ferran Alet, a PhD student at MIT, and this is our work on graph element networks. What does it take to have a good inductive bias? Let's start by considering convolutional neural networks, which is widely agreed to be a useful inductive bias. They are so because they exploit a structural property in the data, mainly locality and translation invariance, and this property is satisfied across a broad set of tasks, mainly computer vision tasks. Let's now consider another type of neural network that's gaining a lot of popularity recently, graph neural networks. They're also a useful inductive bias. In this case, they exploit the fact that entities exist in the world and that we can model them as a graph. This also has broad applications, in this case, modeling entities and their relations. In this work, we present graph element networks, and we argue they're a useful inductive bias by exploiting the fact that in the right space, functions are locally linear, and we show that this is a good inductive bias for tackling function-to-function mappings. Function-to-function mappings is a type of problem setting where the input is a function and the output is also a function. And we will show this has very diverse applications, from which we will show 3 of them in this paper. Let's start with an example. Imagine the Earth and a simplified weather model. We have 2 functions. Our first function defines the humidity and wind today at any point on Earth. So we have one point on Earth, you give me a latitude and a longitude, and I give you the humidity and wind at that coordinate. It's a function defined on the Earth. Therefore, it goes from x, the Earth, to y, the humidity and wind. We call this function f. We have now another function, which is the probability of raining tomorrow at any point on Earth. We call this function g, and it goes from x to z. Notice how fitting any of these functions separately may not be the best idea or may not be very useful. What we actually care about is predicting the function g from the function f. Therefore, we have a function-to-function mapping. More concretely, our algorithm should take a function, x to y, and output another function, x to z. In practice, what we do is instead of handling the analytical form, we handle samples. Our data set, usually in the typical machine learning setting, would consist of xy, y1, x2, y2. In this case, it consists of f1, g1, f2, g2. This is not just a change of letters. In this case, what we mean is that we have functions as our data points. So in the example of the Earth, for example, we would have the humidity function for January 1st, and then the probability, the actual rain the next day, the humidity and wind defined on several points on the Earth for January 2nd, and the rain the next day, and so on and so forth until the humidity and wind for yesterday and the rain for today. Now that we have this data set, at test time, we have the humidity and wind today on several points on the Earth, and now we get a query, and we have to answer what is the probability of rain tomorrow at this query. We could get multiple queries, and queries need not be in the same positions of the samples. They can be queried somewhere else. Our loss function is a bit more complex than the usual loss function. In this case, the algorithm takes in a data set because we have several samples instead of just one point. And it gets evaluated at the query position x sub q and compared against the target g of x sub q. With this, we sum across queries, and then we sum across function pairs in our data set. Let's now take a simplified case where instead of the Earth, we have a square. Now our metric space is a square. We have 2 functions defined on there, the red function and the green function. And our work and our task is to go from the red samples to the green queries. As is typically done in the machine in deep learning, we go through a latent space. So what we will do is we will encode all the samples to the latent space in parallel, and then we hope to decode those samples from the latent space to the output. And then we will be able to make some assumptions in this latent space. One good property of using this latent space is the fact that we can have multiple input functions and multiple output functions, and the only thing that we need to care about is how to encode them and then decode them from this latent space. In practice, though, we can see that we need to separate the input from the output latent spaces, because otherwise the input f at the top left, for example, would not be able to affect the function g at the bottom right. If we do not separate them and we consider them jointly, what happens is that the effect will only be local. So consider, for example, our example from the Earth. We would like a hurricane in Cuba to be able to affect the probability of raining tomorrow in Miami, and not just the probability of raining tomorrow in Cuba. Since effects are global, we will have to somehow propagate the information so that it affects other parts of the space. To do so, what we do is we put both things on a mesh, and we will propagate this information on this mesh via message passing. Therefore, in practice, we only actually have one mesh, and we propagate the information across this mesh. However, the mesh right now does not still have the information about the input. The information is contained on the samples. Therefore, we have to map the information from the samples to the mesh. How do we do it? Well, we can use a representation function that maps samples to nearby points on the mesh, similar to an attention mechanism. And by doing that in parallel across all the data points in the latent space, we can initialize our mesh. Now that we have initialized our mesh and the information on the mesh contains the information on the input, we just need to propagate the information via message passing. Nodes will send the information to their neighbors, receive the information from their neighbors, and update their own state. By doing this repeatedly, we are able to propagate the information across all the mesh. Now that the information is propagated across the mesh, we used, again, the same representation function, but in the reverse way. Now we are able to interpolate the queries in latent space and then decode them to get the final output. OK, now we have defined how the method works. Let's see the parameters. As is usual in deep learning, everything is basically a neural network. So the encoder is a neural network, the decoder is a neural network, and the mesh is a graph neural network, where we have an edge neural network and a node neural network. The edge neural network takes the hidden state of two nodes and computes the message that the first node will send to the second node. The second step now is each node sums the incoming messages from its neighbors, picks its old state, feeds both of them to the node neural network to compute the new state for that node. Now, similar to in how convolutional neural networks, you know that they reuse the same filters across all the positions in an image. Similarly, graph neural networks reuse the same edge neural network and the same node neural network across all the nodes and all the edges in the graph. In practice, for us, what this means is that we have the same edge neural network and the same node neural network shared across all the meshes. So we have one edge neural network and one node neural network shared across the mesh. This has one useful application, which is that we can run the same parameters at different mesh densities, meaning that our mesh need not be the same number of nodes. We can have sparser meshes or denser meshes. If we are willing to spend more compute by having a denser mesh, we will get better accuracy. But note that the same actual parameters, the same neural network weights, are used in both the dense mesh and the sparse mesh. Maybe a more subtle point is the fact that node positions are also a parameter. Because we invented the mesh, we created it, therefore we can initialize them at random and train them by backpropagation to focus the computation where it matters the most. This flexible idea of flexible nodes where we can basically optimize this contrasts with most related work on graph neural networks, where the entities are where the nodes in the graph neural network are tied to entities in the space. This notion of entity is pretty general. It can tackle bouncing balls or particles in objects or joints on simulated characters, but is still fixed. Closer to our domain of interest is the field of geometric deep learning, which analyzes graphs and non-Euclidean manifolds. And within this subfield, there's people that have studied meshes. In this case, however, their meshes are either part of the input or part of the output. But in essence, they are part of the object of interest that they care about. In contrast, we do not care about meshes. We care about input functions and output functions. And our meshes are just a computational substrate that is useful to tackle our problem. This idea was inspired by finite element methods, which is a widely used method in applied mathematics and engineering. These work by decomposing the space into small subregions and approximating partial differential equations inside each subregion. Similar to us, they can run different meshes at different densities and get better accuracies with denser meshes. Since we are inspired by finite element methods, we thought that a good first experiment to try was to do the same application, mainly in this case, learning to solve partial differential equations. So we learned to solve the heat equation, which is one of the most classical partial differential equations. The heat equation has a boundary condition. Imagine it's basically estimating the heat across the room. So we have the heat across the walls, and then we have the placement and power of the heaters in the room. If we now feed both informations across our graph element network, we are able to predict the temperature at any point in the room. In contrast to finite element methods, which would need the actual analytical equation for the partial differential equation, we only need to learn it from many examples. Now, in comparison to our baseline, we can see that already small meshes can already perform very well. And now, if we're willing to spend a bit more compute, we can keep decreasing the error by a lot. And again, I want to insist the fact that we are using the same weights across all the points on the graph. We can also optimize the node positions to focus on the hardest parts of the space to make the computation where it matters the most. If we do that, we can see that already very small meshes do very well because we are focusing the computation where it matters the most. Therefore, small meshes already perform well. The second experiment we wanted to talk about today is based on a work by Islami et al. From last year, which is neural scene representation. The idea is the following. We have several views from a scene. We have poses and we have images. And now you're given a few poses and a few images from those poses. And now you're asked for a new pose. And you have to guess the image from that new pose. To keep the computational tractable, we take the contrastive coding framework, which basically means that we get a few poses and a few images for those poses. We get a query pose, and now instead of rendering the image, which is expensive computationally, we choose one of the candidates among a set of images. Let's see how this fits into our framework. Now, the input function and the output function are the same. And now we use graph element networks as a type of spatial memory. We have an agent moving in the environment, and now when it sees something, it can store in this spatial memory. What happens, though, if we get out of the bedroom and we move out of a kitchen? In the original setting, we only had one scene, but in real life, we may want to move around and explore the world. Note that most neural network architectures have a finite memory or a finite state space. For example, LSTMs always have the same hidden input size. In contrast, now, if we wanted to use graph element networks and we get some measurement outside our mesh, since we are the ones creating this mesh, the only thing that we need to do is expand our mesh, and now we can save the new memory into this spatial memory. To showcase this application, what we did is we picked mazes from the original data set, and we stacked them onto groups of 1 by 1, 2 by 2, but also 3 by 3, 4 by 4, and 5 by 5. We train both the baseline and graph element networks on 1 by 1 and 2 by 2, and ask them to generalize to 3 by 3, 4 by 4, and 5 by 5. We can see that the baseline, but also many architectures with fixed representation, may perform very well at the beginning with small mazes, but now, once we have problems that have much bigger spaces than the ones they were trained on, performance suddenly plummets. Whereas graph element networks, since they can expand the representation very smoothly, they are able to maintain performance. In summary, we proposed a problem setting which is function-to-function mappings, and we showed they have very varied applications. We're able to learn to solve partial differential equations. We also have an experiment doing robotics modeling, which we are not able to show here today. I can talk more about in the poster for time reasons. And then we showed how they can be used as a spatial memory for scene representation. The way we solved it was by combining attention and graph neural networks by meshing the space and propagating the information using graph neural networks. And another key idea is the fact that we are using graph neural networks not to model entities and relations, but as an adaptive computational substrate. This idea of adaptability can take many forms. We're able to focus on the harder regions by optimizing the positions of the nodes in our meshes. We're able to trade between compute and accuracy by choosing at test time which mesh do we want to run, which size do we want to run, and the parameters will always be the same parameters. Or we're able to expand with space size such that if we have to tackle a bigger problem, we just need to increase our meshes. For more information, please come to our poster number 16, or the code and paper is in the website aletetal.com. Thank you for your attention.